Right, so we're going to start. Good morning, everyone. Hope you had a nice weekend. Last night we finished up with gas mixtures, and there were two examples that were still missing. So we'll just go quickly through looking at the solution of these examples. So we'll do together example 2, and I will suggest that example 3 I'll give you some time so you can work out and check whether you have understood how to do this type of problems. Has anyone tried to do this by yourself? No, not any, nobody? Right, so we'll do that later on. And after that, we will start with the other part, the second hour of the lecture, or before, if this shouldn't take that much time. We'll start looking at single gas and liquid flows calculations through a pipe. Okay, so let's have a look. So if you remember, there are two equations that we stated last time, which are used for mixtures, right? So when we want to calculate the properties of the mixture, basically we want to obtain entropy of the mixtures or enthalpy of the mixtures. So the general equations that we have seen is just the sum of the properties of the components of the mixture, but in the case of entropy we have to, so this will be of the components of the mixtures, and then we will have to add taking into account the non-ideality of the system, if you remember. So for an ideal system, what will be the value of this fig? 1, okay? Will be 1. And then taking into account as well the contribution of the mixture into the entropy, right? So that's the general equation that we saw for entropy. And well, you don't need to learn that equation, but you will be given the general equation in the exam, but you will need to know how to use it. And then we looked as well for enthalpy, and enthalpy is a much simpler equation. So we have just the contribution of the enthalpy of each one of the components, and then in case we have a system that cannot be assumed that is an ideal mixture, then we take into account as well the non-ideality of the mixture. Okay, so these were the two equations that we looked at last time. So it's just in one of your slides. I think it's slide number 4. You have the two equations in there, and these are the general ones which can be applied to ideal solutions and non-ideal solutions. So last time we saw an example of how to use these to calculate the entropy and enthalpy of a pure substance. And today we're going to do another example as well, which is basically we want to calculate the entropy and enthalpy of a gas mixture. Okay? So here the problem says that we have propane and propene at 400 kelvins and 2000 kilopascal. The mass fraction of propane is 0.8 and the mass fraction of propene is 0.2. So this time, I think example 1, the mixture was an ideal mixture, and this time the problem states that this mixture is non-ideal. When you are working actually in the field, I mean, nobody's going to tell you treat this as an ideal mixture or as a non-ideal mixture. So we have said that there is some characteristics that we can take into account in order to define because that will be something that we will need to do ourselves, whether the mixture can be treated as ideal or not. So which were those things that we discussed last time? Do you remember? When can we say that a mixture is ideal?
There is no mixture. Pure substance.
Pure substance.
Like
Anyone?
if you don't have like water or gasoline.
Water?
Gasoline.
Okay, why if you don't have water, then you can treat it as ideal, you say. Why? Why is that?
Similar amounts.
The properties of the fuel, but what makes the fuel? Of the fluid?
How do you pose 0.8 for the...
The properties of the fluid. It's not as specific as what I will. The properties of what? The properties of the hydrocarbons of the compounds. The properties of the compounds that makes the mixture. Okay? So if the properties of the compounds that make the mixture are similar, you can treat it as ideal. But it's not because, I mean, if we talk about properties, we're saying enthalpy, entropy. So it's not because of the enthalpy and entropy being the same. So what kind of system are we referring to? What kind of property are we referring to here? Alkane and propane, would that be an ideal mixture?
No. Alkane and propane.
I mean, an alkene is like a propane.
Yes, alkane is a series of propane and other one. Molecular weights. Okay, so if the molecular structures of the compounds that make the mixture are similar, then we can treat it as an ideal. Okay, so if we have a series of alkanes, such as propane, ethane, whatever, mixed together, then it's ideal. If we have water in there, then it doesn't resemble that, and therefore the mixture is non-ideal. Okay, so if we have, let's say, a mixture that not only has a single phase, two phases, gas and liquid, what should we do in order to define if it's a mixture that is ideal or non-ideal?
Like non-ideal.
Like what?
If, for example, easily they have two phases, water and
The liquid?
yeah.
The liquid phase and the gas phase.
Yeah.
Okay, so how would you treat this mixture? How would you define whether it's an ideal mixture or non-ideal mixture? So, non-ideal, you will say, too complicated, non-ideal. But the problem is that if you say everything is not ideal, then you surround yourself by a series of complex equations that will take you quite a lot. I mean, you want a quick answer, then you're going to say, okay, I don't have time to do some modeling at this time. So we want to actually treat the mixtures as ideal if possible. That's our ideal situations as engineers, isn't it? So basically what we're going to do is if we have a mixture which is liquid and gas, we will look at the compounds that are in the liquid, and we will look at the compounds that are in the gas. And we can treat each fraction as ideal separately. Okay? So we'll treat all the liquid because it's likely, let's say, if we have certain temperature, it's likely that, let's say, at that temperature, volatiles has gone to the gas phase. So it's likely that those compounds will have a similar structure. That's why they have volatilized, and that's why they are in the gas phase. And it's likely that the liquids will have more or less the same properties, perhaps heavy hydrocarbons which haven't volatilized. So you can actually divide them and treat the two of them as ideal in the gas phase and ideal in the liquid phase. Okay, so this is something that perhaps in the exam here it's stated, but it's something that it won't be stated. So you will have to look at the properties of the compounds that you are treating in order to how you are going to calculate the properties, the molecular properties to calculate the enthalpy and entropy properties. Okay? So, right. So here we have the example. And basically, what we have found from data, historic data, is the molecular weight of propane, obviously, and the enthalpy and entropy of propane at ideal conditions or atmospheric conditions. And we have the equation that relates Cp to the temperature. Okay, here we're given actually the factors that account into the non-ideality of the system. So phi in this case is 0.883. For the propane, again, we have found the molecular weight, the enthalpy, and the entropy of the propane. And we're given the factors that account for the non-ideality of the system, as well as an equation which relates the calorific, the heat capacity, to the temperature. So now we can basically calculate the entropy and enthalpy of each one of the compounds. Okay? So here, instead of calculating first of propane, then of propene, what we have done for this entropy calculation is just put the two together. Okay, so you can see that this part 0.792 is the mole fraction. Right, here something that you have to check is that the first thing is that you were given a fraction which was a mass fraction, so you need to convert that to molar fraction, and that's how you use the molecular weight, right? So here this has been already calculated to molar fraction, okay, and then we have the equation which accounts into the let's say this will be the entropy at the entropy at the end if we want delta S. If you remember, for a compound we'll have normally delta S equals and the, I don't know, the, what will be Cp dt, Cp over T, like that, no? So, and because this system is not ideal, then we will have to account as well for the non-ideality of the system, which is basically the relations that we have seen here. So here what I wanted to say in this equation is be careful with this delta S, okay? This delta S equals S2 minus S1. So if we want to find out the entropy of the system at the conditions that we are given, then S1 will resemble the conditions that we are given at atmospheric and pressure and temperature, and this S2 will be the actual entropy that we want to calculate. So this part of the equation, this will be S2 and that will be S1, right? So this is the entropy at atmospheric and atmospheric temperature and pressure. And then here we have the derivation or the integration of the parts of the compound. So this will be the actual part of the equation, which is basically this part. Oh well, I have it on the board, so this part of the equation. So art, we have 8.31, T 400, and then that derivative was given by the system, okay? And then we have again R, a natural logarithm of what we have the conditions in there, okay? And this will be for the propane and the propene. We add them together and then we have the entropy of the mixture. And here you can see that the units are either written in joules per mole Kelvin or joules per kilogram Kelvin, depending whether you convert back to mass values. So again, if you have to do this calculation in the exam, please state the units. Because obviously if you don't state the units, we don't know whether the number is correct. It will depend whether you express it as mole of kilograms. So just express them as the simplest way possible, but please write down the units. And then now we go and calculate the mixture of the enthalpy, right? So here we have this enthalpy value, basically, which will be this initial enthalpy that we found. And this is the non-ideality of the system. So that's RT squared and the derivative over here. So here you can see the non-ideality of the system. So you do this for one compound and for the other, and then you have the enthalpy of the mixture. So really, I mean, it's not very difficult, the equations that you have to do for calculated entropy and enthalpy of a mixture. But I think the challenge here is that doing your calculations in an ordered way and expressing everything on the right units. Okay, so this, you can end up with very big equations. Okay, so then we have a liquid mixture. So using the data given below, calculate the enthalpy and entropy of the water solution at 101.3 kilopascal and 45 degrees Celsius. Calculate the same enthalpy and entropy of the same solution, assuming it is an ideal solution. Okay, so we have to calculate it in terms of non-ideal and ideal solution. So can you do the calculations without looking at the answer, just to see whether you'll be able to do that by yourself? So I'll give you 15 minutes. Please do the calculations. I have here some handouts on mixtures, 3. If somebody has not, does anyone requires a handout for this lecture? I only have 3. H2 minus H1. So you generally class H1
When did you get this reverse implication? Reverse implication. When did you get what it was? Reverse
This is the impression of this one. That's what she looks This is liquid mixture. This should be some mixture. This one is liquid.
So the first thing you have to do is change to molar fraction, right? Who has changed to molar fraction? Can you raise your hand? water. Okay, for water. Okay, so you're adding the amount of the okay. That's where the values that were given, the ones that you basically found in the literature were this temperature. So that's atmospheric. Yes, atmospheric temperature and pressure. That will be standard. This is atmospheric. This is atmospheric plus 25 to 98. So one.
We use this one all the time.
No, depending on where you got the values. So you could get, let's see, if you had that and you didn't have any values, you would have to find out some values to help you calculate that. So then you go and search in the literature. And they say, oh, okay, I found the atmospheric pressure and pressure and temperature, the entropy for this condition. Then I'm going to change it to my conditions.
So there is nothing new when we use this.
Well, normally you would be given for problems here, but in real life you will have to find that. So, I don't know, this is... So one of the things to point out here is that you are given the, first of all, entropy and enthalpy at the saturation point of water and ethanol. What is the saturation point? Well, at the boiling point. Okay, so in this case, you are not given the initial conditions at standard pressure and temperature, as you were given in the previous example, right? So in this case, we're actually having the conditions that we found of entropy and enthalpy were at the boiling point of those mixtures. Why? Because normally those are reported in literature. It's very easy to find the enthalpy and entropy of compounds at the saturation point, because normally it's something that is used a lot. Okay? So it doesn't matter which is the initial point or which data you are given, whether it's at standard temperature and pressure, ambient temperature or pressure, saturation point temperature or pressure, or boiling point, you will proceed with the same calculation to find the condition that you want at the temperature that you want to obtain. Okay? So it doesn't always start at the standard temperature and pressure. It can start at any, you can have anything. And why is that? Because imagine that you are given a certain mixture at this temperature and pressure. Okay, they're not going to give you, oh, here is the ambient temperature and pressure of the mixture. So you will have to search that data. You will have to find something as a reference to start your calculations. So you will look in enthalpy charts, you will look in different type of sources when they give you the data of enthalpy and entropy. So in this case, the source that was found, the properties that were found were at the boiling point of ethanol and water. And you found the enthalpy and entropy at the boiling point conditions for these two mixtures. And that's why you start like that. Is this clear? Is this clear, or should I give another example? Clear? Okay, so basically, I'm not going to go through the solution of this, but you will have to apply the same equations that we saw in the previous part. Now, let's have a look at mixture compressor example. Okay? So, in this case, we have seen compressed processes, right? Which is the first assumption that we use when we want to update or to calculate the work required by a compressor. What is one of the assumptions that we use? Okay, no heat transfer in compressors. What else? When we started calculations for compressors, you remember that there was an assumption that we later fixed. Which was that assumption? It's related to entropy. In a compressor, what is the assumption that we make? Same entropy, isentropic. Okay, same entropy at the beginning and at the end. And what does that mean? What does it mean that the same entropy is at the beginning and at the end? Delta S equals to 0. That means that we are assumed first that the compressor is working 100% efficient. Okay, so that's the first thing that we do in the compressor. And later, with the isentropic efficiency, we correct to actually state for the non-efficiency of the compressor. Do you remember? So, in terms of the mixtures, the same calculations will apply. Okay, so we'll follow the same procedure if we have a compressor getting a mixture. The only thing that will change is basically calculating the enthalpy and the entropy at the beginning of the mixture. Right? So basically you will have to perform this calculation the same way, but you will have to do the enthalpy and entropy of the mixture. So let's say we have this mixture containing 80% methane, 10% ethane, 10% of propane at this temperature and pressure, and this is compressed to 6 bar. Okay, so the process can be carried out in two ways. Here we're looking at a two compression mechanism, basically. So compression to 3 bar, cooling at 298, and compression to 6 bar, or compression to 6 bar. So what are we basically looking here? Here we're looking whether it's more feasible to have two compressors in the system or only one compressor. Okay. So how will you determine what is more efficient? What will you look for to determine which one is best? So you look at the work needed, right? So you calculate the work needed for each of the compressors separately, add them up, and compare to the work needed if you only have one compressor, right? So basically here you will look at the work. So both routes use compressors with isentropic efficiency of 75%, and it is assumed that the gas mixture obeys the ideal gas law. Use the data below to calculate the work required for each compression process. So again, here you have methane, ethane, propane, and the CP and the entropies and enthalpies at atmospheric temperature. Okay? So what will be the steps that we will follow to solve these problems? So first, we will find the mixture properties, the entropy and the enthalpy before the compressor. So of this methane, ethane, and propane. Okay? Once we have the mixture properties of these, then we will calculate the compression using isentropic compression to find the temperature after the isentropic compressor. Find the isentropic work to convert to real work. And use the real work to find the temperature after compression. Okay? So that's what we have basically done when we were looking at compression mechanisms. We basically found out first, we always said that during the compression of a gas, the temperature rises. So we'll need to find what is the temperature and what is basically the work that we will need for compression. Okay? So there is an ideal, another thing as well. If you will have a heat exchanger, then you will need to provide certain heat to the heat exchanger in the case of using two compressors. So here you have more or less the solution to go through this. So I will recommend that you go through this solution yourself and then tell me if you have any problems with that. So we will take 10 minutes break, and then we will start with the fluid calculations. Okay, thank you.
Is it solution for this one? For this one?
Write it down. Yes, exactly. Have you finished with the tutorials?
I'm starting.
Okay, so yes, first do the tutorials and then you look at previous papers. Right, I've talked to Nigel, who is going to come to give you the second part of this, one of the parts of this module, and he will come the 8th of March, which is next Thursday. Okay, so you should check in your timetable. Please, if someone can check that actually it appears in your timetable. I think we are going to meet in the Stevenson lecture theaters, and it's going to be like you have some lectures on Thursday, isn't it? Well, you are from several programs, and some of you have lectures on Thursday, so it will be 2 blocks whenever you have time. Does it show up or not?
You said 8.
Thursday, next Thursday, 9. Thursday the 9th.
Okay.
Yes. So first we'll meet from 9 to what? 9 to 12, and after that 2 to 3. Right? I will say, actually it's going to be a very short period of time because he's quite busy and he's only able to come one day. So you have in Blackboard the notes of the lecture that he's going to give you, right? So I would suggest that all of you look at those notes, and if you have a special thing that you basically need to, you have a question or anything and it's not covered, then you ask it at the same time. So I would recommend self-study before he comes here, because it's going to be like 4 hours that he's going to be here for a lot of material. So obviously I'll be there and check what he covers, but in case he doesn't cover certain thing and then it's on the blackboard, please read it before so you can ask and learn as much as possible. Okay, so the objective in here is for you to learn, because he has fresh industrial experience. So any questions you may have, just ask them to him. Okay? So basically, Thursday he will come, and after that, I will give you the assignment. Okay? So yes. So after that, you have enough material, I think, to be able to solve a problem. And the assignment will be submitted after Easter. So you'll have plenty of time to work on the assignment and everything, and to help you. So right now it's an ideal time to do the tutorials before you get the assignment and start worried about the exam. So please finish the tutorials. Okay?
Is he from Shell? You said Shell.
No, he's not from Shell. He's actually from Espen company, which is a Northeast company, but it started in the Northeast and now it's global. It's in several places around the world. And they basically bring consultancy to, they have engineering design projects, and normally perform all the engineering aspects of hydrocarbon extraction, and basically hydrocarbon extraction. Yeah, so a lot of these companies nowadays, Shell and others, they just subcontract small firms to actually do the engineering, and then they are in charge of the operation. So he's in charge of basically the construction and not operation. Okay, so shall we continue? Right. So now we're moving on to another topic, and here we will look at fluid flow in pipes. Okay. So how many of you have already done mechanical energy balances for fluids going in pipes? Can you raise your hand? Energy balances? No? Nobody? I can't believe it. A long time ago.
Can you speak?
Thank you.
I don't remember. Was it?
Yes, well, yes, it's something that you learn for sure. As a chemical engineer, civil engineer. So now it's a little bit of mind freshener or refreshing your already stored knowledge somewhere in your brain of these topics. So we're going to look at fluid flow in pipes for first single phases, and I think that Nigel will tell you a little bit about multi-phase flow. We will look at single phases for gases and liquids. Okay? So basically, hydrocarbons can either be in a gas or a liquid form, and we will look at them independently today and next time. And with Nigel, you will look at multi-phase flow. Multi-phase flow is a very complex system to calculate pressure changes in multi-phase flow, and most of the calculation for multi-phase flow are not based really on theory, but just on correlations, on experience that people have seen in the lab, have looked at it, and basically have derived equations that explain the phenomena that is occurring for a multi-phase flow. Okay, but for single flows, for liquid or gases, we basically can refer to theory in order to help us obtain pressure changes in the system. So here, these are the references in case you would like to explore a little bit more that or have more doubts. So here we have basically a pipeline. We have looked at the processes of valves, of compressors, of pumps, but something that we will most look as well is when the hydrocarbon or fluid goes through the pipeline. While it goes through the pipeline, it will encounter a certain of fittings, and there will be certain forces changing during that. So, first of all, we want to know two things. Basically, how much work is needed to make the fluid flow at a desired rate. So you want certain amount of rate at the end of the pipeline, and if you apply work, whether it's through a pump for a liquid or a compressor for a gas, you want to know how much work you need to apply in order to allow the gas to travel throughout the whole pipeline and arrive at the exit at the required load that you want, as well as for liquid. And another thing is what state is the fluid at the end of the pipeline. Okay, so determine certain what is the pressure of the fluid, what will be the conditions of the fluid going out of that. So, first of all, something that we have already divided in the previous example is that the answer to determine what will be the work that you require depends on a simple assumption that we need to know as well. Whether the fluid is a liquid or a gas vapor. And here when we say liquid or gas vapor, we are basically referring to the compressibility of the fluid, whether the fluid is compressible or incompressible. There are certain liquids at certain conditions that can be compressible fluids as well. But normally, in general, most of the liquids are incompressible. Okay, so we can state with a reasonable assumption that a liquid is an incompressible fluid because if you it has a defined volume which is very difficult to change. While a gas can change its volume very easily through changes of temperature and pressure, and therefore it's defined as a compressible fluid. So for liquid, incompressible flows, the density of the flow is constant. So volume and density, how are they related? Yes, over volume. So density, the inverse of volume will be density, and the inverse of density will be volume. Okay? So they are not directly related, but inversely related, right? So therefore, for a liquid that is incompressible, it won't change its volume. Therefore, the density will be constant. It won't change its density. They are related, right? And now the velocity only changes if the cross-sectional area for flow changes. So therefore, the velocity will be related to the flow, basically, and the temperature of the flow will be constant. It will only change if you have heat transferred to the system. So if you have a heated pipe, or if basically you are transferring heat to the system, okay? So there won't be any significant temperature changes around the pipeline, as well as we have seen for some of the processes as well for liquids. And therefore the density will be constant as well as volume. That's the major characteristic of an incompressible flow for normally, which is assumed in liquids. In the gas and vapor, these are normally compressible flows where the density, velocity, and temperature all change. Okay, so density and temperature will change throughout the movement of the gas in the pipeline, and that will affect basically the characteristics of the pipeline as well as the energy balance, right? So the density is not constant in a gas, and the density can be constant on a liquid. And if we do that, then it will basically change our mathematical equation, whether we need to integrate, how we're going to integrate one and the other. So incompressible flow problems can be solved by using mass and energy balance. So normally we just need the continuity equation, energy mass in equals mass out, and energy balance, Bernoulli equation that perhaps you remember, but if not, we'll look at it. But incompressible flow problems will require mass, momentum, and energy balance as well. Okay, so we'll need to use momentum. So something as well very important is the type of regime that is happening in the pipeline. Okay, so the regime will be normally obtained using the Reynolds number. Okay, so the Reynolds number is something that we are very familiar with, and we know that the Reynolds number helps us define whether a flow is turbulent, whether it's laminar, or whether it's in the middle of these two phases. So if we were having a pipeline, an horizontal pipeline, and then we had a laminar flow, and we suddenly inject a dye, then we will look at very small dispersion of that dye through the y-axis. Okay, so normally the dye will conserve its, let's say, direction, and it won't disperse. And that's because the movement of the liquid is basically as if we were having sheets of liquid going through, and there's no mixture really on the y-axis. in a turbulent flow, we basically have a lot of mixture as well in the y and x direction, so movement of the y direction and in the x direction, and therefore if we were injecting a dye, it will immediately disperse throughout the whole fluid and we'll see a complete change of color. Okay, so for laminar flow, the dye does not spray to the walls because layers of fluid are maintained. And for turbulent flow, the dye spreads to the walls almost immediately due to motion of eddies in the flow. So eddies are basically circular motions, which is the mixture of the flow. So the parameter that tells us whether the flow is laminar or turbulent is called the Reynolds number. So the Reynolds number equals to the density times the velocity and diameter over the viscosity. Okay? So for laminar flow, we normally call a fluid to be laminar when it's a Reynolds number lower than 2,100. For turbulent flow, the Reynolds numbers will be higher than 4,000. And then if it's between the two of them, it's transitional flow. And normally we can use it in order to help us calculate sometimes the friction factor. Okay? So we will see how we use later on the Reynolds number. Okay, so what we're going to do is first we are going to see the very general equation that we use to basically define movement. Okay, so we will start this lecture just defining movement through a pipe, and after that, once we define the forces that basically make a fluid go through it, a little bit going through physics, through momentum, then we will apply that to incompressible fluids and we will apply it to compressible fluids. Okay, so we will start very general through basically a force that makes the liquids go through it. Okay, so I have given you the handout. A handout, and in this handout we will basically see a little bit of momentum. So I want by yourself just to read 1 and 2. I'll give you 5 minutes to read that, and then I'll ask you some questions, and then we'll see if you can answer. So 5 minutes to read 1 and 2 of your handout. Okay, so tell me, what is momentum? Who can tell me? What is momentum? mass times acceleration. So mass times acceleration equals to a force, okay? So momentum is a force. What is the difference between momentum balances, energy balances, and mass balances?
They are related. It's just the difference.
Okay, they are related. All tell us something about the fluid that is going. But what does a mass balance tell us? The mass going in and the mass going out. What does energy tell us? An energy balance. Energy and yes, the energy that we may need in a system, and momentum. The forces we need of the system, the dynamics of the fluid, how the fluid behaves, how the fluid moves. And if we want to know how something moves, then we need to know how fast it moves, but also, what also we need? The direction, okay? So the difference between a mass and energy balance and a momentum balance is that mass and energy balance are scalar properties. They only have a basically number. This is how much energy you need, this is how much mass you have. Momentum is a vectorial quantity that has also a direction. Because we want to obtain the fluid's dynamics, we want to know the fluid dynamics. So we not only need to know what is the velocity of the fluid, but also where the fluid is moving actually. Okay? So momentum is a force, it has a direction, and the way we construct the balance is the same way as we do energy and mass balances. Okay? So this will be in terms of property will be a conservation property. So you have the same, the momentum is constant, and every momentum that goes in should go out. So all the forces that go in will be the forces that will go out of the system depending on how the forces are used in the system. Okay? So a lot of engineers actually look at momentum and their work or their profession is looking at dynamics of the system. So the dynamics of the system, perhaps you have seen, I'm not sure, whether we have a pipe, and then sometimes they show in different colors how the movement is moving, where the fluid is going faster and where the fluid is going slower. And this is basically defining the dynamics of the fluid through a pipeline, and that's basically explaining the momentum of the system. Okay? So here, mass and momentum and energy are all conserved quantities, which means everything that goes into the system goes out. And then we have the same balance equation. Flow into the system minus flow out of the system will be equal to 0. Okay? Now I'll go to your slides. Then I will work on the slides, but I think that you should later on read this if you have more questions, because here is in the handouts it's a little bit more explained. Okay? So we have a pipe. Here we're just going to look at momentum as it is applicable in a pipeline. Okay? So it will be a circular structure, a cylindrical basically vessel, which will reflect the pipeline, and we will not look at momentum at other types of vessels. So here we have the pipe, and then A will be the cross-sectional area of the pipe, which is this area of the pipe. Rho, fluid density, and V, fluid velocity. This will be the diameter of the pipe. And let's say that we want to know the momentum from this inlet to this outlet. So this is the area that we want to study, and that will be the distance traveled by the fluid going through the system. Okay, so for the mass balance, the mass flow rate at any point in the pipe will be given by rho AV. And using the balance again, so rho AV in minus rho AV out will be equal to 0. So if we take the mass balance at the inlet at this point in here, then we can say that rho AV is basically the mass going in the system at x. So x will be the initial point in here. The mass flowing out at point x plus delta x is written to the mass rho AV, mass out, x plus delta x. That will be the mass going out here, once we have passed already delta x, okay? So this is mass going in, mass going out. So therefore the mass balance can be explained like that. Rho AV at the inlet minus rho AV at the outlet equals to 0. Now, by taking the limit of delta x and dividing over a delta x, then we can express this as the differential of density times velocity over dx equals to 0. And that's basically the same way to express this equation. Okay, we have divided by the area here and the limit of delta x. Right? So this will be the mass balance of this of the pipe, of the fluid going through the pipe. Now let's have a look at the momentum balance. Okay? So again, we have the same pipe and we have the cross-sectional area of the pipe, the area of the wall of the pipe. So here it's very important because the momentum will be affected by the cross-sectional area, which is all this circular here, but also the wall of the area, which is basically the area that goes throughout the surface of the wall. Okay? Not only this circle, but actually what will be the external thing. So the momentum of a fluid will be mass flow times velocity, right? So we have said previously that mass flow equals rho AV, right? So if we multiply that times velocity, then we'll have rho AV squared, and that will be momentum. So momentum will be rho AV squared. And this will be the units of force, newtons. So momentum balance is a force balance. So what forces cause the fluid to flow and what retard the flow? Which are the forces that cause the fluid to flow? The forces. Pressure of the fluid, which is the applied force, okay, where we relate the pressure. What else can gravity force? Yes, in case this is an inclined pipe, but it can play both ways. It can retard or make it fluid to flow depending on the direction of the flow. And what is the force retarding the flow? Friction of the pipe. Okay? So basically those are the forces that we are going to see reflected in a momentum balance. So balancing all the forces. So here we have momentum in minus momentum out. So here in is x, out is x plus delta x, as we have seen. This is the pressure forces that we have in the system at the inlet and at the outlet. This will be the gravity force in the system. And this will be the friction force, which is basically expressed by the area of the wall. Here, very carefully, this area of the wall is not the same as the cross-sectional area of the pipe. Okay? So it will be a different value times the shear stress, which is the tau. Okay? So that will be the friction of the wall. Right? So again, if we divide that over the area of the cross-sectional area of the wall, delta x, and taking the limit of delta x to 0, then the cross-sectional, we can basically substitute as well the cross-sectional area of the pipe and the wall area of the pipe, which by their basically area, how we calculate the area of each one. So the cross-sectional area will be of a circle, and the other one will be more of a cylinder or of a wall. So that, or the other one will be, yes. So that the area of the wall can be expressed over the diameter. Okay, so we are just trying to substitute these values into the big equation to be able to express the equation by the diameter instead of the area of the wall. So if we take the limit, we are able to express the momentum of this fluid flow in pipes using this derivative. Okay, so the change of momentum in the pipeline will be equal to the change of pressure in the pipeline plus the gravity forces minus the shear stress caused in the pipe. Okay, so that's basically the momentum balance for the pipe. Now here, this is density times the gravity. If this was inclined, if these pipes wasn't completely horizontal but had an inclination, what will be here? How this factor will be modified? What would you add here? If the pipe wasn't completely horizontal and then we had an inclined pipe, how will this equation be modified? No, Z, no. Well, Z you will basically have an inclination. So how would you modify this equation? No. So if you have the pipe like that, you have an angle, right? So how would you put the angle in here? So you will multiply the gravity times the cosine of the angle, of the sine of the angle, okay? In order to get the actual reflection of the gravity force in the pipeline, right? Is that all right? But this is for an horizontal pipe where you have a fluid going through it. So the fluid, now let's refer to the energy balance, okay? So not momentum balance, but energy balance, right? So the energy balance of the segment of a fluid, then we have the kinetic energy that is applied to the system, which is basically the velocity, the square of the velocity over 2, and the internal energy of the fluid going through that. So both units of energy per units mass. Energy flow is found by multiplying the energy per unit mass by the mass flow. Okay, so this is basically just the units of the fluid, and in this case we'll basically use whatever is affecting the system in terms of energy. So what will be the energy balance? What will constitute the energy balance? So we have kinetic energy, we have internal energy, but in this case that will be, let's say, if we have a pipe that is not insulated and there is a heat flow between the outlet and the interior, then we'll have some changes in energy, of internal energy of the fluid. It will change its temperature because of that. And what else? What else do we have? Can we have there? So we have the kinetic energy, internal energy, but then we also use the energy factors that we use in the momentum. So we have the potential energy and the pressure energy. Okay? So the energy balance of a fluid flow in pipes will be somehow overimposed by the momentum balance, because the energy will use some of the forces that were used as well in the energy balance, in the momentum balance. So we have the energy flow at X will be the mass times the velocity that is coming in the system and the internal energy that the fluid has. Okay, so that's the energy at which we have in X. The pressure energy in X will be the pressure times the area and velocity here. The potential gravity or energy at X will be the momentum times the area, velocity, gravity, and Z. And then we have the energy dissipated by friction and energy transfer through the wall. So this is what is happening in this place. Okay, so the energy dissipated by friction will be here, and the energy transfer through the walls will be here. The energy flow out of the system, what is going out in here, will be again the same, the mass times the velocity that we have in here and the internal energy of the system. Here, I think in these slides, we are referring as the internal energy as a E. And previously, when we were looking, we actually refer as a U. Okay, so you can change that and put it at U. I think in your handout, I also refer it as a U. So it just depends on the convention. In some mechanical engineering books, this is referred as an E. But actually, in thermodynamics, this is referred as a U. Okay, so this is the internal energy that we are talking about. The pressure energy at the outlet of the system and the potential energy. So this is the overall energy balance of the system, okay? So we have the whatever is coming in the energy, in the inlet, and then we have to add the pressure energy and the potential energy. So basically this will be in, that will be out. It doesn't change at all, and the only thing that change are the energy dissipated by friction through the distance of the fluid going through the pipeline and the energy transfer through the walls in case the pipeline was not insulated. So then we input all these factors in the general equation, in minus out, okay, equals accumulation. So we have here the inlet, and we have put them all together, the outlet all together, the changes of pressure, the friction factor, the friction losses through the system, and the heat transfer. All these should be equal to 0 in order to obey the conservation law. Okay. So taking the limit as delta x tends to 0, then we end up with this derivation basically. So the changes of the energy in the system will be equal to the changes of pressure minus the changes in friction, minus the friction, minus the heat, plus the heat flow. Okay? And here it's very important that you change, that the signs can change depending whether you have energy going in, energy going out of the system. So if we look at this part of the equation, what does it resemble to here? The Bernoulli equation, okay? So we're approximating to that. Now, this will be the general energy equation for my pipe. This energy equation can be applicable to a compressible or an incompressible fluid, right? Is that all right? Have any questions? Perhaps someone else has the same question.
Yeah. We divided by A delta x and then applied the limit delta x equal to 0.
Yes.
Yeah. Then the parameter d, how did it come from?
This derivative?
No, the right side, the last two. Denominator, yeah.
If you remember, we said that the area of the wall and the area can also be expressed in terms of the diameter. So there are two equations separately. A cross-sectional area of the pipe is not the same as area of the wall. Since there are two variables, we can basically substitute that by the corresponding equation of diameter, and therefore we end up with only one variable, which is diameter. Okay. So basically here, what is not shown is all the workings to go that. But if you go through the handout, I've tried to show all the workings. So you can go and see really how the equations were derived. Right? But this is basically the derivative of the general equation that will be applicable to compressible or incompressible fluids. Now we're going to sort of use this equation and try to apply it to incompressible fluids, liquids, and everything will be very simple. So, basically, in an incompressible fluid, then we can, for an incompressible fluid, we said that the density is constant and the temperature is constant. Okay, how we started these lectures. And if the temperature is constant, therefore the internal energy E or U will also be constant, assuming no significant heat transfer through the pipe walls. So for incompressible fluid flow, mass and momentum balance reduced to the following. Okay, so this was the initial mass balance. In this case, density doesn't change through the fluid going through that. We said density is constant, so it went out of the derivative, and as well as the area. The area of the pipeline will be constant. So therefore, we have dV over dx. Okay, so the only thing that changes will be kind of the velocity. And this will be equal to 0. The momentum balance also goes to this expression. And if we substitute these two into the overall energy balance that we saw previously, then we end up with this equation, okay? So if we substitute the mass balance and momentum balance in this equation that we saw here, then we end up with this much simpler energy balance, right? So if we end up with this simpler energy balance, this equation says that the change in mechanical energy for an isothermal fluid flow is caused by friction. So the energy balance says that the mechanical energy for an isothermal fluid is caused by friction only. So therefore, we can end up, if we take out the derivative, we have it as a derivative of this factor. So instead of having it as a derivative, we have it as a 1 and 2, okay, inlet and outlet. Therefore, we can express it as the inlet, the energy at the inlet, equals the energy at the outlet plus the friction. And that's basically the Bernoulli equation. So normally, instead of using this, we just use HF, which is the friction that we have in the pipeline, the friction loss that we have in the pipeline. So normally, this equation can be either expressed in meters or in terms of energy, joules per kilogram. In general, in most of the engineering aspects, most in pipelines, when we're referring pipelines, they always tell you in meters, okay? So we normally look in head losses, head pressure, head, and always when we say head, it's always meters. So we all divide by the gravity, and when by dividing by the gravity, we basically convert everything to meters, and it's easier, it's a more gentle unit, and then everybody understands them. But it's the same thing, okay? The last term at the right is called the loss due to HF. So this was the friction that we said. So this is how physics look at friction. And I think this is how engineers look at friction. So a little bit more simpler. But actually it's the shear stress, the tau, which is causing the friction. So the work added by the system by a pump is not included in this equation. So here we're looking only at friction, and basically this will be a little bit resembled by the general equation. So if we look at the work, looking in the given into the system, then we can add the work, the shaft work given into the system, again over gravity, because we want to express it as meters as well. Okay, so work in meters, which is very funny, but it's very easy to work like that in terms of the mechanical energy balance. So here we have the energy in equals the energy out plus the friction losses plus the work that is given. right? And this will be the general mechanical energy balance that we'll use for a liquid. And this is how we're going to solve all the 5 problems where we have a fluid that is a liquid going through a pipeline. So do you understand what all these variables mean? Okay. Right, so we not only have to take into account the friction in pipes, but also in fittings. So how are we going to look at the friction in pipes in fittings? Okay, so we have accounted for friction in terms of wall shear stress, but we basically are going to account it as the frictional force in the walls. Okay? So basically, in here, we will sort of look at it as the pressure losses that occur due to friction. And in order to do that, we'll define the changes in pressure in the pipeline that occur towards the changes in friction. And sorry, I think this U should be velocity. Okay, so change that with V. That's velocity. So basically the changes in pressure that will be provided because of friction losses, how much pressure you're going to lose in your system because of these friction losses, is given by the friction factor, but what we call the friction factor, multiplied by L over D. So L is delta X, is the length that we are going through the pipeline, density V squared, the velocity of the system.
Why 2?
Huh? 2? That depends a lot of where the friction factor comes from. There are 2 types of charts where the friction factor can come from. The Fanning friction factor or the Darcy friction factor. Okay? So depending on that, you will either multiply by 2 or you will actually divide by 2. And this is something very important because you will see in books that in some of them they divide by 2 or they multiply by 2. But actually you have what we call the FD and the FF. Okay? And one of them will be a quarter of the other. And this is why it ends up like that. But it's explained in the handout as well. I try to explain what is the difference between FD and FF. So if you go in the handout, that's in page 10, page 10. So page 10 of the handout, here we have the friction factor using the Darcy equation and the Fanning friction factor. And actually in some books they don't tell you whether it's Fanning or Darcy, they just say F, which is sometimes confusing because these 2 changes actually whether the F is obtained from one and the other. But then if you look at the chart, page 11 you have the Fanning friction factor chart, okay? So whenever you don't know what type of F is being provided from the chart that you are looking, you always have to look at the laminar region, okay? The laminar region is always very nicely, and it's always a slope and a straight line, an inclined line. It doesn't change a lot. And you look at the slope of the laminar region. So in this case, the laminar flow is 16 over Reynolds, okay? And 16 over Reynolds is normally for Fanning friction factor. If you have 64 over Reynolds, then it's Darcy friction factor. So if you are provided with this chart, or you find this chart and you don't know, it's not specified whether it is a Fanning or Darcy friction factor, look at the laminar flow at the slope and look at how this slope is defined. So if it's 16 over the Reynolds, that will be a Fanning friction factor. 64 over the Reynolds, Darcy friction factor. So that will be that Fanning friction factor will be the friction factor of Darcy over 4, right? So the Darcy friction factor will be 4 times the fanning friction factor. And that is reflected here. So here why we multiply by 2? Because we want to sort of compensate for the fanning friction factor. So here we are using fanning friction factor.
Yeah, why not 4?
Because it comes from the derivation. I think that you end up with 2D, something about substituting here the area of the wall, and then you end 4/2, then 2. So you have to do the substitution of the area of the wall in there. So all this is already like worked out for you. Yeah, so you have this for here. So this equation is based on experimental data, and F is called the friction factor is correlated to experimental data as a function of Reynolds number. So, who has seen this chart before? Can you raise your hand if you have seen that? Nobody?
Long time.
No, well, not this one, but let's say the friction factor chart before. Yes? Okay. So here you can see the Reynolds number and the friction factor, how it is related. For a laminar flow, it's a very straight line, very easy, but for turbulent flow, then what we have to take into account for turbulent flow? The roughness of the pipeline, the relative roughness, okay? And the relative roughness will be the roughness over the diameter. So you take the relative roughness, the Reynolds, and then obtain the friction factor of the chart, input that into the equation, and then take the pressure changes due to the friction of the fluid. So that's the same friction factor chart. That, well, here it's very complex because it's very detailed, but this will be a summary. Okay, and it comes. This chart, especially for the turbulent regions, from the Colebrook equation. So if you didn't want to use this chart and you wanted to input everything in a mathematical software, you will input that equation and solve that equation for the friction factor. Well, yes, if you have a computer, but if you want to do it completely like that, it's better to use the chart. So relative roughness is absolute roughness of the pipe diameter, and the absolute roughness is normally known for a range of pipe materials. So it will depend whether it's stainless steel, carbon, or what type of material you're using for the pipe. Right, so we'll stop here, and then we can continue on fittings next time. Please go through these handouts by yourself, and next Monday, if you ask me any questions on that, we can go through it in more detail. Okay? See you then. Yes, it is a lot of them. Yes, although I don't think that you will have any type of problems like that in the exam. It's far too long, but anyway, you can have it too.
Maybe I will work as a process assurance engineer.
Oh, that's good. Yes.
But I'm a reliability engineer, so I should know everything.
You're a what?
Reliability engineer. Working in a shell reliability.
Oh, really?
We're doing everything. We should know everything.
What do you use in your work?
No, but I mean, we have lead for that. We are working with discipline engineers, like process engineers, mechanical engineers, instrumentation engineers, so electrical engineers. We are doing like fault risk assessments, root cause analysis, for some failures, for example. Maybe if it might be process failure, it might be mechanical failure. So we should
yeah, so it's going to be useful for what you're doing. That's great.
I asked you what he wrote this review and
Yes. The coursework I'll give it to you next week. I think you were away while I made the announcement during the break. Yes, I made the announcement that next week we're going to have a lecture on Thursday. So check your timetable because Nigel from the industry, he's going to come to give his class. We'll only be here like for 4 hours, but actually it's a lot of information, so it's recommended for you to read through those handouts before. It's from 9 to 12 and then from 1 to 2. So it doesn't overlap, or? Yes, yes, it's Thursday during that timing. And then after that, I will give the assignments, and then you will have to return the assignment after Easter.
Yeah, because I noticed we've got a slot for the computer.
But that's not, yes, it is.
First week after Easter.
Yes, but that's for give you the practical on the simulation.
Right, okay.
So that's for you just to know the software. I'm not sure if you have used before HISIS. So we are going to see HISIS, but you don't have to apply it in your assignment. Your assignment will be separate from that. So that's just for you to know that software.
Right, brilliant.
Okay,
Thank
see
you
you.
very much.
Bye-bye.
Cheers, mate.
I think that was an option.
But it says that if someone, an agent has agreed to send the situation review, have it.